Every atom in your body was forged inside a star. So where did the very first spark of life come from? We are about to journey to the edge of time, exploring 30 incredible theories for the origin of the universe's first organic molecules. You will discover how the fundamental ingredients for life may have been cooked in the hearts of distant nebulae, delivered by violent cosmic impacts, or assembled in the deep ocean's darkness. Was our existence sparked by a lightning strike in a primordial soup, or did it sail to Earth on a frozen comet from another world? How do you think the story of our cosmic beginnings truly unfolded? Our story begins not in the stars, but in the steamy, turbulent conditions of a newborn Earth. The air was thick with a potent mix of gases, methane, ammonia, and water vapor, swirling above a global ocean that was anything but tranquil. This is the stage for our first theory, the concept of a primordial soup. In the 1920s, two scientists independently proposed a breathtakingly simple idea. Alexander Oparin and J.B.S. Haldane suggested that this early environment, charged with energy from relentless lightning strikes and the sun's intense ultraviolet radiation, could have been a vast chemical laboratory. In this chaotic brew, the simple inorganic compounds in the atmosphere and sea might have been jolted into forming the very first building blocks of life, amino acids. For decades, this remained an elegant but unproven hypothesis. Then, in the 1950s, a young graduate student named Stanley Miller, working with his professor Hydrothermal, decided to put this idea to the test. They built a remarkable apparatus designed to mimic the ancient Earth. One flask held water, representing the early ocean, while another was filled with the proposed early atmospheric gases. Then they sent sparks of electricity, simulating lightning, coursing through the gaseous mixture. After just 1 week, the results were stunning. The once clear water had turned a murky red and brown. An analysis revealed that it was now rich with organic compounds, including several different amino acids, the fundamental components of proteins. This single experiment, the Miller-Urey experiment, sent shockwaves through the scientific community. It provided the first tangible evidence that the basic ingredients for life could arise naturally from non-living matter, given the right planetary conditions. It suggested that the spark of life might not be a miraculous event, but a chemical inevitability, a fundamental process written into the very laws of the universe. Yet this surface world, crackling with lightning, was also a place of extreme peril. The young sun bathed the planet in lethal levels of ultraviolet radiation, a force that could easily shatter the delicate organic molecules being forged in the atmosphere. So where could this fragile chemistry find a safe haven to develop and grow? The answer may lie in the one place shielded from the chaos above, in the eternal darkness of the deep ocean. Here at the bottom of the sea, another kind of furnace was at work. Towering mineral chimneys, known as black smokers, spew superheated water, rich with dissolved metals and sulfur from fissures in the Earth's crust. These vents are oases of extreme chemistry, where the planet's internal heat provides a constant, powerful energy source, completely independent of the sun. The porous rock of the vent structures acts as a natural catalyst, a kind of microscopic scaffolding where simple molecules can gather and be encouraged to link into more complex chains. But there is another, perhaps even more promising type of vent. Alkaline vents, also called white smokers, are less about intense heat and more about a profound chemical difference. They release warm, mineral-rich fluids that are highly alkaline, contrasting sharply with the acidic ocean water. This difference creates a natural electrical charge, a proton gradient, which is the same fundamental energy currency that powers every living cell today. Within the labyrinth of microscopic pores in these rocky structures, a protected environment exists. Here, the building blocks of life, like amino acids and fatty acids, could have concentrated and assembled, shielded from the destructive forces on the surface. This theory suggests that life did not begin in a sun-drenched soup, but in the deep, hot, and chemically rich heart of the planet itself, finding its first foothold in the dark, pressurized silence of the abyss. But what if the ingredients for Earth's first life were not even made on Earth? This leads us to a truly cosmic theory, the idea of Panspermia. This concept suggests that the fundamental building blocks of life, or perhaps even the earliest living organisms themselves, did not originate on our planet. Instead, they hitched a ride through the solar system, delivered to a receptive Earth by celestial travelers. Imagine comets, asteroids, and even fine interstellar dust grains acting as cosmic taxis, ferrying the seeds of life across the vast emptiness of space. These objects could have provided a protective shell, shielding their fragile organic cargo from the harsh radiation and extreme temperatures of the void during their long journeys. The most compelling evidence for this theory comes from meteorites that have fallen to Earth, specifically a type known as carbonaceous chondrites. One of the most famous is the Murchison meteorite, which landed in Australia in 1969. When scientists analyzed its composition, they were astonished. Locked within that ancient space rock was a rich and diverse array of organic compounds, including over 90 different amino acids, some of which are the very same ones used by life on our planet. Even more remarkably, these meteorites contained nucleobases, the critical information carrying components of DNA and RNA. This proved beyond any doubt that the complex chemistry needed for life is not unique to Earth. The universe itself is a prolific organic chemist, synthesizing these molecules in the frigid clouds of gas and dust between the stars, and on the surfaces of asteroids as they drift through the cosmos. So, the water in your body may have come from comets, and the very letters of your genetic code might have been written in the heart of a distant nebula, long before our world even formed. These cosmic deliveries point to a profound truth. The chemistry of life begins not on planets, but in the cold, dark voids between the stars. Drifting through our galaxy are immense, silent clouds of gas and dust so vast they could swallow entire solar systems. These are the interstellar molecular clouds, the true nurseries of stars and planets, and they are also incredible chemical factories. Within their frigid depths, where temperatures hover just a few degrees above absolute zero, a quiet miracle of construction is constantly underway. The key to this process is the tiniest of components, microscopic dust grains composed of silicate rock or carbon, finer than smoke. These grains act as cosmic workbenches. In the emptiness of space, simple atoms like carbon, oxygen, and hydrogen would rarely collide and stick together. But on the cold, solid surface of a dust grain, they can land and stay, slowly migrating across the surface until they meet another atom and form a bond. Layer by layer, molecule by molecule, these surfaces build up complexity. This is how some of the most important organic molecules in the universe are forged. Scientists using powerful radio telescopes have identified the chemical signatures of polycyclic aromatic hydrocarbons, or PAHs, within these clouds. These are large, sturdy molecules made of interconnected rings of carbon and hydrogen, essentially the fundamental soot from which more complex structures can grow. Even more astonishingly, they have detected simple sugars like glycolaldehyde, a molecule directly involved in the formation of RNA. This means that the very sweet, fundamental units for genetic material are being cooked up in deep space long before they ever reach a planet. Far from being an empty void, the space between stars is a bustling, productive chemical laboratory, silently manufacturing the essential ingredients that planets like Earth simply inherit, bringing us one step closer to understanding how a sterile universe can become a living one. Even in the deep freeze of a molecular cloud, there is a constant invisible rain. High-energy radiation, from cosmic rays to the harsh light of newborn stars, relentlessly bombards those tiny dust grains and their fragile icy coatings. This is not a destructive force, but a creative one. When a high-energy particle or photon smashes into a simple ice molecule like frozen water, methane, or ammonia, it can shatter chemical bonds in a flash. The resulting fragments are highly reactive radicals desperate to form new connections. In the chaotic instant following the impact, these broken pieces reassemble into something entirely new and far more complex. This process, known as radiative processing, builds molecules that simple chemistry could never produce in the cold void alone. We have seen the stunning results of this cosmic alchemy up close. When the European Space Agency's Rosetta probe analyzed Comet 67P, it discovered a rich inventory of organic compounds, including the amino acid glycine. This simple brick of life was likely forged in the ices of that very comet, cooked by millions of years of cosmic radiation as it journeyed through the outer solar system. This same process is almost certainly at work right now on the frozen moons of Jupiter and Saturn. The icy surfaces of worlds like Europa and Enceladus are bathed in intense radiation from their giant parent planets. Beneath their frozen crusts in vast subsurface oceans, the complex organics created on the surface could be slowly raining down, providing the raw ingredients for life in alien seas. This theory suggests that the universe has a universal recipe for organic chemistry. Take simple ices, add a steady dose of radiation, and wait. The resulting molecular complexity could be the default setting for countless worlds across the galaxy, a silent, continuous process that seeds the cosmos with life's potential. The violence that threatened to shatter early life may have been the very force that created it. While radiation works its quiet magic in deep space, here on the young Earth a far more dramatic process was unfolding. The planet was under constant bombardment, a celestial shooting gallery where asteroids and comets slammed into the surface with unimaginable force. Each impact was a cataclysm, but within that destructive fury lay a creative spark. This is the theory of shock synthesis. When a massive object strikes a planet, it does not just leave a crater. It generates a blistering shock wave that races through the atmosphere at thousands of miles per hour. This wave compresses the air in front of it to an incredible density, superheating it to temperatures hotter than the surface of the sun, all in a fleeting, violent instant. Within this temporary inferno, the simple gases of the early atmosphere, like methane, ammonia, and water vapor, are ripped apart and violently reassembled. The extreme pressure and heat force them into new, more complex arrangements, forging the very organic molecules that were previously absent. Scientists have tested this explosive recipe in the laboratory. Using powerful guns that fire projectiles at incredible speeds into gas mixtures designed to mimic the primordial atmosphere, they have recreated these fleeting moments of impact. The results are definitive. From these miniature, man-made cataclysms, a rich soup of organic compounds emerges, including the all-important amino acids. It is a paradox of the highest order. The same apocalyptic impacts that could have sterilized the planet, boiling away oceans and scouring the land, may have simultaneously seeded it with the essential ingredients for life. This paints a picture of a world where creation and destruction were two sides of the same coin, and where life's first building blocks were born in fire and thunder. But the leap from simple molecules to a complex, self-replicating system is a chasm that seems almost impossible to cross. How could chemistry bridge that gap without a guiding hand? The answer might lie not in the water or the air, but in the mud. The theory of clay mineral catalysis proposes that the very ground beneath our feet provided the first stage for life's most critical act. Imagine the quiet, mineral-rich shores of a volcanic pond on the early Earth. Here, a particular type of clay known as montmorillonite forms in fine, flat sheets. Its surface is not smooth, but is covered in a precise, repeating pattern of positive and negative electrical charges, a landscape of molecular hills and valleys. This structure makes it a powerful catalyst, a substance that speeds up chemical reactions without being consumed itself. In this primordial environment, simple organic molecules drifting in the water would be naturally attracted to and concentrated on the clay's charged surface. The clay does more than just gather them together. It acts as a template, a molecular mold. Its orderly crystalline structure forces the building blocks of life to align in specific ways, encouraging them to link up into long, complex chains. This process is especially crucial for the formation of ribonucleic acid, or RNA, a molecule considered by many to be the original spark of life, capable of both storing genetic information and catalyzing its own replication. Laboratory experiments have shown this is not just speculation. When researchers provide the basic components of RNA in the presence of these clays, the minerals dramatically accelerate the formation of long RNA chains, some reaching lengths of 50 units or more. The mud, it seems, is not just dirt. It is a creative force, a natural assembly line that could have taken the scattered Lego bricks of organic chemistry and, piece by piece, began building the first instruction manual for life itself. These clays provided a stage, but the performance of life requires more than just assembly. It needs energy, a constant driving force to sustain its intricate chemical dances. This brings us back to the deep sea vents, but with a radical new perspective from the late 1980s. German chemist Gunther Wechterscheuser proposed a theory that turned the search for life's origins on its head. He called it the iron-sulfur world, a metabolism-first hypothesis. Forget about genes or replication for a moment. What if life began not as a molecule that could copy itself, but as a simple, self-sustaining cycle of chemical reactions, a primitive metabolism that fed upon itself to grow? The engine for this system was a mineral so common it is known as fool's gold, pyrite. At the alkaline hydrothermal vents we discussed earlier, Wechterscheuser imagined a dramatic scene. Hot, mineral-rich fluids laden with hydrogen sulfide and dissolved metals surge up from the Earth's crust and meet the colder, acidic ocean water. In this chemical clash, tiny crystals of iron pyrite begin to form. The surface of a growing pyrite crystal is a place of immense chemical power. It has a positively charged, highly structured surface, and its formation actually releases energy. Think of it as a naturally occurring charged battery plate. Wechterscheuser proposed that simple organic molecules like carbon dioxide could be drawn to and locked onto this reactive pyrite surface. Using the energy released from the pyrite's own formation, these simple molecules could be reduced or gain electrons, kick-starting a cascade of reactions. This could form the core of a two-dimensional chemistry, a metabolic cycle clinging to the mineral's surface that constantly converts incoming gases into more complex organic compounds, such as acetic acid or pyruvic acid, which are fundamental to modern biochemistry. This is a profound departure from the idea of life starting with a self-replicating RNA molecule. In the iron-sulfur world, replication comes later. The primary goal is persistence, a chemical system that can maintain itself, grow, and spread across the mineral surface, all powered by geochemistry. It is a vision of life's precursor not as a solitary molecule floating in a soup, but as a vibrant, energetic film, a living rust that learned to feed on the very rock it called home. The ground itself seemed to be trying to build life, but a crucial piece was still missing. How could a chemical system not only sustain itself, but also remember how to do it and pass that knowledge on? The answer may lie in a single, remarkable molecule, the star of a theory known as the RNA world. This concept suggests that the very first life form was not a cell, but a strand of ribonucleic acid, or RNA. What makes RNA so special is its stunning duality. Like its more famous cousin DNA, it can store genetic information, acting as a set of instructions. But unlike the relatively passive DNA, RNA can also act as an enzyme, a catalyst that speeds up chemical reactions. We call these catalytic RNA molecules ribozymes. Think of it as a single molecule that is both the architect and the construction worker, capable of both designing a blueprint and then actively building the structure itself. A self-replicating RNA molecule in the early oceans would have been a revolutionary entity. It could copy itself, and because copying is never perfect, errors would creep in. Some of these new versions would be better at replicating than others, launching the entire, breathtaking process of evolution by natural selection. This was chemistry beginning to learn, to adapt, and to remember. But this elegant theory faces its own monumental question. Where did the first RNA molecules come from? RNA is a complex polymer built from smaller units called nucleotides. Each nucleotide is itself an intricate structure, requiring a sugar, a phosphate, and a nitrogenous base to link together in just the right way. The spontaneous formation of such sophisticated components in the primordial soup seems incredibly unlikely. This is where our previous theories converge to offer possible solutions. Perhaps the nucleotides were forged elsewhere. The formamide-based chemistry we explored earlier, where a simple solvent concentrates energy and building blocks, could have been the crucible. Alternatively, the nucleobases, the informational parts of the nucleotides, could have been delivered pre-made, raining down upon Earth from carbon-rich meteorites. The RNA world does not stand alone. It is the potential climax of a long cosmic story, a story that began with interstellar dust grains and asteroid impacts, progressed through mineral catalysts and metabolic films, and finally achieved a moment of critical self-awareness with a molecule that could look upon its own structure and decide to make another. High above the stormy chaos of the young Earth's surface, a different kind of chemical laboratory was at work, bathed in the sun's unfiltered glare. The upper atmosphere was a realm of constant, invisible transformation, where ultraviolet light served as both destroyer and creator. This intense radiation, the same force that made the surface so perilous for early molecules, possessed the precise energy needed to shatter stable gases. When a photon of ultraviolet light strikes a molecule of carbon dioxide or molecular nitrogen, it can break the chemical bonds holding it together. This violent splitting produces a shower of highly reactive fragments known as radicals, atoms or molecules with unpaired electrons that are desperate to form new connections. In the thin air high above the planet, these radicals constantly collide and combine, their frantic dance forging some of the most important molecular precursors for life. From this energetic chaos emerge compounds like formaldehyde and hydrogen cyanide. These are not amino acids themselves, but their fundamental blueprints, the simple frameworks from which the entire architecture of biology can be built. Hydrogen cyanide, a molecule infamous for its toxicity today, is a versatile chemical hub, its structure a key ingredient for forming the nucleobases that make up genetic code. Formaldehyde readily links up into sugars, including the ribose that forms the backbone of RNA. This process creates a slow, steady rain of organic material from the sky, a gentle fallout of life's potential that supplements the more violent deliveries from impacts and vents. It suggests that our planet was not just a passive recipient of organic gifts, but an active participant in its own creation, using the very power of its star to cook the recipe for life in the thin, sun-drenched air at the edge of space. The universe's grandest chemistry experiment operates on the smallest of stages. These are not gleaming laboratories, but microscopic specks of cosmic dust, finer than powdered sugar, adrift in the unimaginable cold between the stars. On these tiny grains of silicate and carbon, time itself becomes a reagent. Over millions, even billions of years, a patient and silent construction project unfolds. An atom of carbon, drifting through the void by some infinitesimal chance, bumps into a dust grain and sticks. Then an oxygen atom lands nearby. In the deep freeze of space, these atoms do not bounce away. They slowly, glacially migrate across the surface of the grain. When they finally meet, they form a bond, creating a simple molecule of carbon monoxide. This process repeats molecule by molecule, layer by layer, building up a fragile mantle of ices like water, methane, and ammonia. The dust grain is more than just a passive platform. Its crystalline structure provides a template, a landscape of atomic hills and valleys that guides how new arrivals orient themselves, encouraging specific chemical marriages that would be impossible in the empty space around it. This is surface chemistry on a cosmic scale. The slow, relentless accretion transforms a simple grain into a complex organic refinery, where formaldehyde can link into sugars and hydrogen cyanide can weave itself into the ringed structures of nucleobases. These microscopic particles are the universe's primary workshops, proving that complexity is not born in a flash, but assembled with infinite patience, one meticulous reaction at a time. The quiet, patient chemistry of cosmic dust grains requires a starting material, a simple seed from which the forest of life can grow. That seed might be a single, unassuming molecule known as formamide. This compound, essentially a molecule of water where one hydrogen is replaced by an organic group, is far more than it seems. It is a chemical chameleon, a universal precursor that scientists now believe could be the master key to unlocking the entire suite of life's building blocks. Formamide is not rare. Its spectral signature has been detected in the vast molecular clouds of deep space and within the glowing tails of comets. It is a cosmic commonplace, and its structure is a perfect chemical hub. With just 4 atoms, 1 nitrogen, 1 carbon, 1 oxygen, and 3 hydrogens, it contains all the essential elements needed to construct the nucleobases for DNA, the amino acids for proteins, and even the fatty components for cell membranes. The question was whether this potential could be unlocked under plausible early Earth conditions. The answer came from the laboratory. Researchers took this simple liquid and subjected it to gentle heat, no more than the temperature of a cup of coffee, in the presence of common terrestrial minerals like clays and metal oxides. These minerals acted as catalysts, guiding the reactions without being consumed. The results were nothing short of spectacular. From this single, primordial soup of formamide, the laboratory flasks began to yield a treasure trove of biomolecules. They detected adenine and guanine, 2 of the 4 crucial nucleobases that spell out our genetic code. They found amino acids like glycine, the simplest of the protein builders. Most astonishingly, they even produced the molecular backbones for lipids, the compounds that naturally form the membranes of every living cell. This is a profoundly unifying idea. Instead of separate, unlikely pathways for creating genetic material, proteins, and cell walls, the formamide reaction network suggests a single, elegant chemical highway. A pool of this simple solvent, warmed by geothermal heat or even just the sun, and enriched with common minerals, could have become a prolific factory for life's essential ingredients. It offers a vision of a planet where the leap from chemistry to biology was not a series of miracles, but a logical, almost inevitable progression from one potent molecule. Deep beneath the surface, another powerful engine was driving the planet's chemistry. The very rocks of the early Earth were still hot with the radioactive decay of elements like uranium and potassium-40. This internal heat did not just create volcanoes, it powered a unique and stable environment for life's origins, the nuclear geyser. Imagine a subterranean chamber where water, seeping down from the surface, is warmed not by magma, but by the steady, relentless glow of radioactive elements in the surrounding rock. This heated water, rich with dissolved minerals from the crust, would periodically erupt to the surface, creating a geyser much like those in Yellowstone today, but powered by atomic decay rather than volcanic fire. This cycle of eruption, cooling, and recharge created a perfect natural laboratory. The geyser's pool provided a wet phase where simple organic molecules, perhaps delivered by meteorites or formed in the atmosphere, could mix and react with mineral catalysts like clays and metal sulfides leaching from the rock. Then, during dry phases as the pool evaporated under the sun, these molecules would become intensely concentrated, a crucial step that encourages them to link together into long polymers, the chains that form the backbone of RNA and proteins. This model elegantly combines the best of many worlds. It offers the protective, mineral-rich environment of a subsurface system, shielded from harmful surface radiation. It provides a constant geothermal energy source that could last for millions of years, far more stable than the fleeting violence of lightning strikes or asteroid impacts. And it introduces the vital cycle of wet and dry phases, a rhythmic pump that drives molecular complexity forward. The nuclear geyser is not just another location. It is a persistent, self-regulating incubator, a cradle where the universe's raw ingredients could be patiently stirred and concentrated for eons, slowly inching across the threshold from chemistry to biology. The quiet construction of cosmic dust grains was only the beginning of the story. For life to truly take hold, these ingredients needed a delivery service, and the solar system provided one in abundance. Among the most promising carriers are the carbon-rich asteroids, known as C-type asteroids. These dark, primitive bodies are the untouched remnants of the solar system's birth, time capsules preserving the original recipe of our cosmic neighborhood. They are thought to be the source of most carbonaceous chondrite meteorites found on Earth, but studying a meteorite that has crashed through our atmosphere is not the same as examining a pristine sample. This is why the Japanese space agency JAXA launched the Hayabusa 2 mission. Its goal was audacious: to travel to a diamond-shaped asteroid named Ryugu, land on its surface, collect material, and bring it home. When the spacecraft finally returned its precious cargo to Earth in 2020, scientists eagerly analyzed the jet-black grains. The results were unequivocal. Locked within that ancient rock, which had never been exposed to Earth's environment, was a rich inventory of organic molecules. Most critically, they confirmed the presence of more than 20 different amino acids, including several, like alanine and glycine, that are directly used by terrestrial life. This was not a suggestion, it was a confirmation. The building blocks of our proteins were not only present in the early solar system, they were already assembled and waiting on the very rocks that would later coalesce to form our planet. This means the organic synthesis of life's fundamental components was a widespread common process, occurring on countless asteroids as they drifted in the darkness, millions of years before Earth itself had even finished cooling. Our planetary cradle was not sterile, it was pre-stocked with the very essence of life, delivered by the celestial rubble from which it was born. Yet the asteroids were not the only carriers in our early solar system. Comets, those ancient, icy wanderers from the outermost dark, carried an even richer and more volatile cargo. Often described as dirty snowballs, their nuclei are a frozen archive of ice, rock dust, and an astonishingly complex cocktail of organic molecules. When these cosmic icebergs swing closer to the sun, their frozen hearts awaken. The heat triggers a spectacular transformation, vaporizing ices to form the brilliant comas and sweeping tails we see in our night sky. But deeper within the nucleus, a more subtle and profound process may be at work. Heat from the sun, or even from the decay of radioactive elements like aluminum-26 that were present in the early solar system, could have melted pockets of ice deep inside the largest comets. For millions of years, as these objects journeyed through the cold void, they could have harbored secret, transient oceans of liquid water, encapsulated within their rocky, insulating interiors. In these dark, watery pockets, the pre-assembled organics delivered by the comet itself, amino acids, nucleobases, and PAHs, would have been dissolved and mobilized. Suddenly, the chemistry is no longer frozen in place. In a liquid water environment, these molecules can mingle, react, and form even more complex structures. The porous rock and clay-like minerals within the comet's core would have provided perfect catalytic surfaces, guiding the formation of peptides and perhaps even the first short chains of RNA. This transforms our view of a comet from a simple delivery truck into a fully equipped flying laboratory. It did not just carry the ingredients for life, it actively cooked them along the way, performing billions of years of delicate probiotic chemistry in the deep freeze of interstellar space, all within its own shielded, watery chambers. But all these molecules and membranes and metabolic cycles were missing one final critical ingredient. Life runs on a kind of chemical currency, a molecule that stores and transfers energy in every cell on Earth. This is adenosine triphosphate, or ATP, and its backbone, like the backbone of DNA itself, is built around the element phosphorus. This presents a profound puzzle for life's origins. On the early Earth, phosphorus was largely locked away in insoluble minerals, trapped in rocks that would not readily dissolve in water. How could this essential element have been freed to power the first living systems? The answer may have fallen from the sky in the form of a rare metallic mineral called schreibersite. This iron-nickel phosphide is commonly found in iron meteorites, and it possesses a remarkable property. Unlike its terrestrial cousins, schreibersite is highly reactive with water. When a meteorite containing this mineral landed in a warm pond or a shallow sea, the schreibersite within it would have begun to corrode, releasing its phosphorus into the water in a soluble, reactive form. Laboratory experiments have vividly recreated this ancient delivery. When researchers place pieces of schreibersite in water that mimics the conditions of the early Earth, the mineral doesn't just dissolve. It actively participates in chemistry, reacting to form a variety of organophosphates. These are the molecular bridges that link phosphorus to the carbon-based frameworks of life. In these experiments, the phosphorus from the meteoritic mineral readily incorporates into the fundamental structures of life, forming the phosphate groups that would eventually become the energy-carrying ATP and the structural backbone of genetic molecules. This suggests that the very spark of energy that animates every living thing and the very chain that holds our genetic code together might have required a delivery from beyond our world. The lifeblood of biology, it seems, was forged in the hearts of metallic asteroids, arriving on Earth as a gift wrapped in cosmic iron. These alkaline vents, with their strange, life-giving chemistry, are powered by a geological process as ancient as the oceans themselves. Deep beneath the seafloor, a fundamental transformation is constantly underway, a reaction between water and the very foundation of the planet. This is serpentinization. When seawater seeps down through cracks in the oceanic crust, it encounters rocks from the Earth's upper mantle like olivine. The water reacts with these iron and magnesium-rich minerals, completely altering their structure and turning them into a new, greenish mineral called serpentine. But this mineralogical makeover is only half the story. The reaction is exothermic, releasing a tremendous amount of heat that warms the surrounding waters. More crucially, it is a chemical power plant in its own right. The process strips oxygen from the water molecules, releasing vast quantities of hydrogen gas. It also produces methane and creates fluids that are highly alkaline, devoid of oxygen, and rich in dissolved minerals. This is not just a simple mixing of rock and water, it is the genesis of a potent prebiotic elixir. These hot, alkaline fluids, now buoyant and charged with chemical potential, rise back up through the crust. They seek out weaknesses, eventually venting into the cold, acidic ocean to form spectacular structures like the Lost City Hydrothermal Field, a ghostly landscape of towering white carbonate chimneys in the mid-Atlantic. The true magic happens at the interface, where this strongly reducing alkaline fluid meets the mildly acidic carbon dioxide-rich ocean water. This meeting creates a natural battery, a proton gradient across the vent's porous walls. But it also does something even more profound for the origin of life. The hydrogen gas produced by serpentinization is a powerful reducing agent, eager to donate electrons. When this hydrogen encounters carbon dioxide dissolved in the ocean water, the conditions are thermodynamically perfect for a remarkable transformation. The carbon dioxide is reduced, its atoms reshuffled with hydrogen to form fundamental organic molecules. This is not a one-time event sparked by a lightning bolt or an impact. It is a continuous, relentless flow. The vent system acts as a natural, non-stop chemical reactor, constantly pumping out hydrogen and methane, and constantly converting the planet's abundant carbon dioxide into the raw carbon-based building blocks for life. Here, the energy was not a fleeting flash but a stable, geologically sustained current, a driving force that could have powered chemical evolution for thousands, even millions of years, patiently assembling complexity in the eternal dark. But this grand dance of molecules needed a stage, a protected space where all this new chemistry could unfold without simply drifting apart. This brings us to a fascinating alternative vision of life's dawn, the lipid world. While the RNA world focuses on information and replication as the starting point, the lipid world suggests that the very first step was not to remember but to separate. It proposes that self-assembling lipid molecules, simple fatty acids, were the true pioneers. In the warm, shallow pools of the early Earth, these fatty acids would have been abundant. When agitated by waves or even just by the natural movement of water, these molecules do something almost magical. They spontaneously organize themselves into tiny, hollow spheres called vesicles. Picture a soap bubble but far more stable and structured, with a double layer of molecules forming its skin. This is a protocell, the most basic possible container. The formation of this simple barrier, this division between an inside and an outside, is a monumental leap. It creates the first individuality, a pocket of the universe that is now distinct from its surroundings. Inside this microscopic bubble, the building blocks of life, like amino acids and nucleobases, could be concentrated and protected. Chemical reactions could proceed in a controlled environment, no longer at the mercy of infinite dilution in the vast ocean. But these lipid membranes were far from passive bags. They were dynamic and active participants. Certain types of fatty acid membranes are surprisingly permeable, allowing small nutrient molecules to drift in while keeping larger, newly formed polymers trapped inside. Some can even grow and divide on their own, simply through the physical stress of being pushed against minerals or agitated by currents. This creates a primitive form of reproduction entirely without genetic instructions. The lipid world presents a compelling path. Before the first gene was ever copied, before the first metabolic cycle spun into action, the simple physical act of forming a boundary may have set the stage for everything that followed. It suggests that the cell itself, the fundamental unit of all life, came first. Far from the sun's warmth, in the deep freeze of the outer solar system, a world utterly alien to our own offers a second recipe for life's beginnings. Saturn's largest moon, Titan, is shrouded in a thick, hazy orange atmosphere, a swirling canvas of organic chemistry. Here, rivers and vast lakes etch the landscape, but they are not filled with water. They are pools of liquid methane and ethane, flowing at temperatures hundreds of degrees below zero. This frigid environment is a natural laboratory for alternative probiotic chemistry, a test of whether life's building blocks can arise in a solvent other than water. High in Titan's atmosphere, solar ultraviolet radiation performs the same creative destruction it did on the early Earth, but with a different cast of characters. It breaks apart methane and nitrogen molecules, and the resulting fragments recombine into increasingly large and complex organic compounds. These molecules clump together to form what scientists call tholins, reddish-brown organic aerosols that give Titan its characteristic haze. This organic smog does not stay aloft forever. It slowly drifts down, coating the moon's surface in a continuous, gentle rain of complex probiotic material. Imagine a world where the foundational ingredients for life are not brewed in a warm pond, but condense out of a frigid sky, settling into lakes of liquefied natural gas. The chemistry that unfolds in these methane seas is fundamentally different from water-based reactions. Molecules that would be unstable or react instantly in water could persist for much longer in this cold, non-polar solvent, allowing for entirely new pathways of chemical complexity to emerge. The Cassini-Huygens mission confirmed this spectacularly, detecting these complex organics in the atmosphere and on the surface. Titan stands as a powerful testament to the universality of organic chemistry. It proves that the universe's drive toward complexity is not limited to warm, watery worlds like our own. The same physical laws that built life on Earth are actively at work in this frozen realm, tirelessly assembling the pieces of a puzzle we are only beginning to understand. While the deep sea vents worked in total darkness, another environment on the early Earth offered a perfect marriage of light and mineral power. The zinc world hypothesis focuses on a seemingly ordinary mineral with extraordinary abilities, zinc sulfide. In the shallow coastal waters near hydrothermal vents, particularly in volcanic settings, crystals of zinc sulfide would have precipitated out in abundance, forming glittering crusts on the rocky surfaces. These tiny crystals are semiconductors, much like the materials in a solar panel, and this property made them a unique catalyst for life's dawn. When exposed to the sun's ultraviolet light, which was far more intense on the young Earth, these ZNS crystals would have absorbed that light energy with incredible efficiency. This energy energizes electrons on the crystal's surface, creating a powerful reducing force capable of driving chemical reactions that would otherwise be impossible in a watery environment. This process could have been the engine for carbon fixation, taking simple, inert carbon dioxide dissolved in the seawater and using the sun's power to reduce it, attaching it to other molecules to build the first organic scaffolds. The range of potential products is vast, from simple formaldehyde to more complex molecules like pyruvic acid, a cornerstone of modern metabolism. This theory elegantly solves two major problems at once. It provides a continuous, renewable energy source courtesy of the sun, and it offers a stable, solid surface, the zinc sulfide crystal, to guide and concentrate the chemistry. It suggests that the very first metabolic processes, the ancient pathways that would eventually power cells, might not have begun in the dark abyss, but in the sun-drenched shallows on the surfaces of minerals that acted as the first solar cells, harnessing the light of a young star to ignite the chemistry of life. While the sun and planetary chemistry provided powerful local forges, the universe itself was bombarding the early Earth with an invisible rain of high-energy particles from deep space. These are galactic cosmic rays, atomic nuclei stripped of their electrons and accelerated to nearly the speed of light by distant supernova and black holes. They represent a third, universal engine for prebiotic chemistry, one that operates everywhere, from the depths of interstellar clouds to the upper reaches of any world with an atmosphere. When one of these high-energy projectiles smashes into a molecule within a dense gas cloud or a planet's air, it does not just break bonds like ultraviolet light might. It violently rips electrons away from the molecule, creating a highly charged, unstable ion. This ionization event is like tossing a rock into a still pond, sending out ripples of chemical reactivity. The newly formed ion is desperate to regain its electronic stability, and it will snatch electrons or rearrange its bonds with nearby molecules in a frantic cascade, initiating unique reaction chains that simpler energy sources cannot spark. This process can build complexity from the bottom up. For instance, a cosmic ray could ionize a simple, abundant molecule like molecular hydrogen in a cloud. This hydrogen ion could then transfer its charge to a carbon monoxide molecule, which then reacts with another hydrogen to ultimately form formaldehyde, a fundamental precursor to sugars. This is not a gentle simmering, but a chemistry of sudden, violent triggers that open new pathways to organic complexity. The power of this theory is its sheer universality. Cosmic rays permeate the galaxy, penetrating environments that other forms of energy cannot reach. They work in the cold, dark interiors of molecular clouds where starlight is too weak to drive chemistry. They reach the surfaces of icy moons and asteroids, even those without a protective atmosphere. On the early Earth, they would have constantly peppered the upper atmosphere, adding their unique, ionizing spark to the mix of processes already brewing life's recipe. This means that on countless worlds across the cosmos, this relentless, invisible drizzle of high-energy particles could be the final ingredient, the match that lights the fire of chemical complexity, proving that the universe is not just building life's ingredients, but is actively, everywhere, trying to set them ablaze. Amidst this cosmic storm of creation, a different kind of architectural genius was silently at work. Scattered across the galaxy are immense, flat molecules built from rings of carbon and hydrogen, known as polycyclic aromatic hydrocarbons. These are not mere specks of dust, they are stable, sturdy platforms, the molecular equivalent of flat, packed furniture for building life. The PAH world hypothesis suggests these abundant cosmic bricks were not just ingredients but the very first workbenches. Their flat, stackable structure is their secret power. In the quiet of space or the shallow pools of a young planet, these molecules would naturally clump together, piling up like microscopic stacks of pancakes. The spaces between these stacks create sheltered nooks and crannies, perfect environments for other, more fragile molecules to gather and be protected. Think of a PAH stack as a molecular scaffold, a temporary framework that holds all the pieces in the right place for assembly. This organized arrangement could have been crucial for guiding the formation of the very first information-carrying molecules. Some PAHs even have a slight electrical charge at their edges, attracting specific chemical groups and acting as a template, forcing amino acids or nucleotides to line up in the correct order to form longer chains. It is a profoundly simple idea. Before the intricate dance of RNA or the formation of lipid membranes, the universe may have been using these robust, carbon-based tiles to lay the foundation. They provided the initial order, the first hint of structure in a chaotic chemical soup, demonstrating that sometimes the most important step in creating something new is just having a stable surface on which to build. A volcanic plume is a planetary engine in its rawest form. On the early Earth, these colossal eruptions did more than just spew lava. They constructed a temporary chemical factory in the sky, a churning, turbulent environment ripe for forging life's precursors. Inside the plume, a superheated mixture of gases like carbon dioxide, nitrogen, sulfur dioxide, and water vapor collided with fine, abrasive particles of volcanic ash. This ash was far from inert. Its jagged, mineral-rich surfaces provided countless catalytic sites, much like the clays we discussed earlier, offering a solid stage where fleeting gas molecules could meet and react. But the true catalyst was the plume's own internal chaos. The violent updrafts, extreme temperature gradients, and intense static charges generated within the ash cloud produced a near-constant display of volcanic lightning. These electrical discharges, far more powerful than any surface storm, sent shock waves of energy through the gaseous cocktail. This single environment masterfully combined the key elements of several other theories. It had the gaseous ingredients and electrical energy of the Miller-Urey experiment, the superheated shock waves of impact synthesis, and the powerful mineral catalysis of surface reactions, all operating simultaneously within a vast, natural reactor that could tower for miles into the atmosphere. As the plume cooled and its contents rained back down to Earth, it would have delivered a rich fallout of newly formed organic compounds directly into the planet's early oceans and lakes. This theory suggests that the very forces that shaped our planet's most violent landscapes were also, paradoxically, among its most prolific creators, turning each eruption into a potential fountain of life's building blocks, showering the young world with complexity from above. Sulfur carries a faint scent of volcanoes and the deep sea, a whisper of the planet's fiery heart, and it may have been the essential spark for life's very first metabolic fires. This element is far more than a simple ingredient. It is a dynamic chemical chameleon, capable of accepting and donating electrons with ease, making it a perfect catalyst and energy currency for primitive biochemistry. Today, sulfur sits at the core of countless enzymes and cofactors that drive the machinery of every living cell, a legacy pointing directly back to its foundational role. Theories now suggest that simple sulfur compounds like hydrogen sulfide bubbling from volcanic vents or mineral sulfides such as pyrite were not just present on the early Earth, they were active participants. They could have provided both the scaffolding and the fuel for the first self-sustaining chemical cycles. The most compelling evidence for this lies in a structure so ancient it is still embedded in our cells, the iron-sulfur cluster. These are tiny, mineral-like arrangements of iron and sulfur atoms that are absolutely central to how modern cells convert energy. They form the reactive core of key proteins involved in respiration and photosynthesis, acting as nature's universal electrical switches. The fact that these inorganic mineral structures are so deeply integrated into the most fundamental processes of biology is a powerful clue. It implies that life did not invent these clusters from scratch, but instead co-opted them, building its first sophisticated machinery directly upon a geochemical foundation that was already operating. The first metabolic pathways may have literally been circuits of electrons flowing across films of iron sulfide minerals, a primitive energy grid powered by the planet's own geochemistry, long before the first cell ever learned to harness the sun. The vast global ocean presented a crushing problem for the first sparks of life. Even if amino acids and nucleobases were raining from the sky or bubbling from the vents, they would be instantly diluted in a body of water trillions of times larger than all our modern seas combined. In such an infinite soup, the chance that two specific molecules would ever find each other and react was vanishingly small. Life needed a way to cheat dilution, to gather its scattered building blocks into a concentrated, potent brew. The solution may have been as simple as a puddle left behind by the tide. Picture a rocky, volcanic coastline on the early Earth, where the daily rhythm of the tides created countless shallow lagoons and tidal pools. These pools became natural concentration factories. Each day, the sun beat down, evaporating the water and leaving behind every dissolved organic molecule in a far richer solution. Over countless cycles, these pools would have become incredibly salty and acidic, a harsh but intensely productive environment where molecules were forced into close quarters, dramatically increasing the odds they would link up. This evaporation is only half the story. In colder regions or during the planet's frigid nights, a different kind of concentration occurred. When a body of water freezes, it does so pure, pushing impurities and dissolved compounds out of the forming ice crystals. These expelled molecules become trapped in the tiny, briny channels between the ice crystals, a network of microscopic tubes where their concentration can skyrocket to levels thousands of times higher than in the open ocean. This is the cold trap, a natural molecular sieve that gathers life's ingredients into a dense, reactive paste. Scientists have recreated these conditions in the lab, taking a dilute solution of amino acids and subjecting it to cycles of freezing and thawing. The results are clear and compelling. The simple amino acids readily link together, forming long protein-like chains called peptides. This process, which might take eons in the open ocean, happens with remarkable efficiency in these frozen reactors. The cold trap theory transforms a planetary liability into an asset. The very vastness of the ocean, once a barrier, now becomes a massive collection network, its currents delivering organic treasures to these quiet shoreline incubators. In these unassuming pools at the edge of the world, the universe patiently concentrated its recipe, drop by drop, until the chemistry was finally strong enough to begin. The Murchison meteorite is more than a rock. It is a message from a time before our planet was born. When it fractured the sky over Australia in 1969, it delivered a stunningly detailed inventory of the cosmos's chemical creativity. Inside that carbon-rich chondrite, scientists found not just a handful of familiar amino acids, but a sprawling family of them, over 100 distinct varieties. Some were the very same molecules that build every protein in your body, like glycine and alanine. Yet the majority were completely alien molecular structures not used by any known life form on Earth. This is the meteorite's most profound revelation. The universe is not just making life's building blocks, it is experimenting with every possible permutation, exploring a vast chemical landscape far wider than the narrow path biology eventually chose. This incredible diversity is tangible, physical proof that complex organic synthesis is not a rare planetary quirk, but a fundamental and rampant process woven into the fabric of interstellar space. The Murchison meteorite directly connects the dots between the theoretical chemistry of distant molecular clouds and the concrete reality of our own origins. Its contents are the end product of millions of years of patient assembly on cosmic dust grains and processing by starlight and cosmic rays. This single stone validates the grand narrative that our solar system, and likely countless others, formed from raw materials that were already preloaded with life's essential code. The legacy of Murchison is undeniable. We are not alone in the universe because life is out there. We are alone because the very ingredients for life are the universe's default setting, a cosmic inheritance written in stone and ice. Long before Earth was even a glimmer of dust, our entire solar system was a single, swirling crucible of creation. This was the protoplanetary disk, a vast, flattened cloud of gas and dust rotating around our infant sun. It was not a uniform haze, but a dynamic, planet-wide chemical reactor, its conditions shifting dramatically with distance from the newborn star's fierce heat. Close to the sun, temperatures were searing enough to vaporize all but the most refractory materials, creating a hot zone where only metals and silicates could condense into solid rock. But further out, beyond a boundary known as the frost line, a profound transition occurred. Here, the sun's warmth was too weak to prevent volatile compounds from freezing. Water, carbon monoxide, methane, and ammonia all crystallized into grains of ice, joining the swirling dust. This single temperature gradient effectively sorted the entire future of the solar system, predetermining which worlds would be rocky and which would become icy giants. Yet the chemistry did not stop at simple freezing. Throughout this entire disk, from its hot inner regions to its frigid outer edges, a constant rain of solar and cosmic radiation provided the energy to drive molecular complexity. In the warmer, gaseous zones closer to the sun, photochemistry similar to that in planetary atmospheres could build up simple organic precursors. Further out in the colder, icy regions, the same radiative processing that occurs in interstellar clouds continued unabated, building complex molecules on the surfaces of frozen dust grains. This meant that different regions of the disk were essentially different chemical factories, each producing its own unique blend of probiotic ingredients. The carbon-rich asteroids that would later deliver amino acids to Earth were forged in the middle regions of this disk, where temperatures were moderate enough for complex organics to survive. The icy comets, carrying their cargo of preserved interstellar ices and complex tholins, were assembled in the freezing darkness of the outer disk, so when the planets finally coalesced from this material, they were not blank slates. Each world was seeded from the very beginning with a specific suite of chemical compounds, a unique inheritance from its orbital birthplace within the grand disk. Earth did not have to invent the chemistry of life from nothing. It formed directly from a reservoir of material that the protoplanetary disk had already spent millions of years pre-processing, setting the stage for everything that was to come. Before the elegant efficiency of ATP, life needed a simpler, more robust energy currency. Christian de Duve, a Nobel laureate who dedicated his life to understanding the cell's inner workings, proposed a compelling answer: the thioester world. This theory suggests that the true molecular glue holding the first metabolic systems together was not a complex nucleotide, but a humble sulfur-containing compound known as a thioester. These molecules are remarkably easy to form under prebiotic conditions, likely arising spontaneously in the same volcanic, sulfur-rich environments that fostered iron sulfide minerals. A thioester forms when a carboxylic acid, a common organic molecule, links to a thiol, the smelly sulfur compound found in everything from hot springs to rotten eggs. What makes this bond so special is its energy. The thioester bond is a high-energy connection, unstable and eager to break, and in doing so, it releases a jolt of energy that can be harnessed to drive other chemical reactions. This is the crucial spark earlier metabolism needed. Think of thioesters as the universal power adapters of prebiotic chemistry. Their energy could have been used to force simple amino acids to link together into the first protein-like chains, or to stitch together the components of nucleotides. They offer a plausible, all-purpose engine for building the complex polymers of life, all without requiring the sophisticated machinery of the modern cell. The thioester world presents a powerful metabolism-first scenario, a stage where energy flow and molecular construction came first. It paints a picture of a nascent biosphere already humming with activity, powered by the simple, potent chemistry of sulfur, long before the first gene ever thought to copy itself. The stability of ribose is a riddle that has long haunted the search for life's origins. This simple sugar is the central spine of the RNA molecule, the scaffold that holds the genetic code together. Yet, in the warm, watery conditions of the early Earth, ribose is notoriously fragile, breaking down in a geological blink of an eye. How could such an evanescent molecule have ever survived long enough to form the first strands of genetic material? The answer might lie in an element you probably associate more with laundry detergent than with Genesis, the element boron. Boron has a unique chemical personality, a kind of molecular sociability that allows it to form stable complexes with ribose. When a boron atom encounters a ribose molecule, it essentially acts as a protective brace, locking the sugar into a specific, stable shape that resists degradation. This single interaction could have been the difference between a fleeting possibility and a lasting reality for RNA world, but this creates another puzzle. On the early Earth, boron was not abundant in the environments where life likely brewed. It was largely locked away in continental rocks that were only just beginning to form. So where did this crucial stabilizing agent come from? The evidence points to the sky. Analysis of meteorites, particularly the famous Murchison meteorite, has revealed the presence of boron within their ancient matrices. It seems that this vital element was another gift from our cosmic construction crew, delivered directly to the reaction chambers of our planet's first ponds and seas. Boron's role did not end with mere stabilization. By holding ribose in a specific configuration, it would have guided the sugar's reactions with phosphate and nucleobases, ensuring that the components of RN are linked together in the correct functional way. It acted as a molecular midwife, ensuring the successful birth of the first genetic molecules, and boron did not work alone. Another element, molybdenum, was waiting in the wings. This metal is a powerhouse catalyst, essential in modern enzymes that manage the flow of electrons in fundamental processes like nitrogen fixation. Molybdenum is exceptionally rare in Earth's crust, yet it is absolutely critical for life. How did it become so central? The answer, once again, appears to be extraterrestrial. Molybdenum, in its soluble, bioavailable form, was likely another passenger on carbonaceous chondrites. When these meteorites dissolved in the early Earth's waters, they released a trace but potent supply of this catalytic metal. In the chemical milieu of a formamide-rich pool or near a hydrothermal vent, molybdenum could have acted as a primitive enzyme, its surface providing a platform to catalyze key redox reactions, perhaps helping to convert inert atmospheric nitrogen into usable ammonia, a fundamental step for building amino acids and nucleobases. The confluence of these two rare elements paints a startling picture. It suggests that the transition from chemistry to biology required a very specific and perhaps finely tuned set of ingredients. Not just the common stuff of carbon and water, but a precise pinch of cosmic spice. The arrival of boron and molybdenum via meteorite might have been the final, delicate turn of the key that unlocked the door to life, a reminder that our existence could hinge on the most subtle and specific of cosmic deliveries. The final theory takes us beyond chemistry and into the realm of cosmic philosophy. When we piece together all these pathways from interstellar dust to volcanic plumes, a profound pattern emerges. The sheer number of viable routes suggests that the universe is not merely capable of creating life's ingredients, it is overwhelmingly inclined to do so. This is the cosmic probability argument, an application of the anthropic principle to the puzzle of abiogenesis. The principle, in its simplest form, observes that the universe must have properties that allow life to arise because we are here to observe it. Our existence is not a miraculous fluke, but a data point in a cosmos of staggering scale and age. With trillions of planets and billions of years at its disposal, the universe functions as the ultimate laboratory. The laws of physics and chemistry are not neutral, they contain a built-in bias toward complexity. Given a reservoir of carbon, a solvent like water, and a few reliable energy sources, the formation of organic molecules becomes a near certainty. The spontaneous assembly of amino acids and nucleobases is not a rare event waiting for a perfect storm of conditions. It is the default outcome of matter organizing itself under these universal rules. We are the living proof of this relentless process. Every atom in your body, every strand of your DNA, is the current, temporary product of a cosmic experiment that has been running for over 13 billion years. The story of our beginnings is not one of incredible luck, but of inevitable consequence, written into the fundamental code of reality itself. So many roads seem to lead to the same destination. With 30 potential pathways for the origin of life's molecules, the question is no longer which one is correct, but how they all work together. These theories are not competing explanations, but interconnected chapters in a single epic story. The true narrative of life's dawn is a grand synthesis, a chain of cosmic events where each process handed off its molecular creations to the next. It begins in the silent, frigid nurseries of interstellar space, where dust grains patiently assemble simple organic molecules. These complex compounds then become frozen into the hearts of comets and asteroids, which act as celestial freighters, delivering their precious cargo across the young solar system. When these objects bombarded the early Earth, they deposited not only water and amino acids, but also the critical, rare elements like boron and molybdenum. On our planet, this cosmic inheritance found a world perfectly primed for chemistry. The violent energy of impacts and volcanic plumes forged new molecules in the atmosphere, which then rained down into the global ocean. There, the gentle, rhythmic cycles of tidal pools and icy brines concentrated these scattered ingredients, while the catalytic power of clay minerals and zinc sulfide crystals provided the scaffolds for assembly. In the eternal darkness of the deep ocean, alkaline hydrothermal vents offered a stable, energy-rich refuge, their porous rocks acting as natural reactors where lipid membranes could form and primitive metabolic cycles could hum to life, powered by the planet's own geochemistry. It was in this collaborative cauldron that the final, miraculous leap could occur. The building blocks from space, concentrated by the planet and assembled on minerals, finally gave rise to a self-replicating molecule, perhaps RNA, that could remember the recipe and begin the adventure of evolution. The journey from stardust to a living cell was not a single miracle, but a symphony of countless ordinary processes, each playing its essential part in the universe's most profound collaboration. From the cold void between stars to the violent heart of a young planet, this journey reveals a universe teeming with potential. The story of our first organic molecules is not a search for a single magical moment, but the unraveling of a cosmic symphony. Each theory, from the quiet assembly on interstellar dust to the roaring chemistry of volcanic plumes, plays its own essential part. The fundamental takeaway is breathtakingly clear. The universe is not a sterile emptiness, but a profoundly creative force. The laws of physics and chemistry are inherently biased toward complexity, constantly weaving simple atoms into the rich tapestry of organic matter. We are not the result of a lucky accident, but the living, breathing expression of a cosmic inevitability. Every element in your body was forged in a star, and every process that assembled those elements into the first spark of life is still at work today, in the dark oceans of icy moons and the hazy skies of distant worlds. You are not just living on a planet, you are the universe itself, becoming conscious and looking back at its own origins. So tell us, which of these incredible pathways resonates most with you? Was it the delivery from the stars, the deep earth chemistry of the vents, or the patient assembly on mineral scaffolds? Share your thoughts in the comments below, and let's continue this grand conversation about where we all truly